Here we have a situation where we've got a mapping, first of all, from zx to z, taking an arbitrary polynomial with integer coefficients and mapping it to an element of z, mapping it to an integer. We're defining it to map an arbitrary polynomial to its value at 0. By the way, the fact that we're mapping it to its value at 0 is kind of arbitrary. We could have picked something other than 0, like f of 5, for example, here. Why is this a ring homomorphism? We've actually done this kind of thing before. We got to verify it's doubly operation preserving. We got to verify that if we add two polynomials and apply phi to that sum, that we get the same thing as phi of the first polynomial plus phi of the second, and also the similar kind of property for multiplication. There's nothing much to do here. By definition of the function f of x plus g of x, what is that function? You add the values, you get f of 0 plus g of 0. But each of those things individually are function values at 0. The first one being phi of f of x, the second one being phi of g of x. Not much to say there. It's essentially just the definition of what phi is and the definition of function addition. Similar kind of thing for multiplication of functions. We get f of 0 times g of 0 here, and each of those individually is an output for phi. The first one is phi of f of x. The second one is phi of g of x. So there's not much to do. Why is the kernel of phi equal to the principal ideal generated by x? If f of x is in the kernel, that means phi of f of x, which by definition is phi of 0, equals 0. To be in the kernel means you get mapped to 0. The additive identity of the codomain here, which is the integers. But we've thought about this before. That means 0 is a root of f of x. That means f of x is x times some other polynomial. I can factor out an x. Called that other polynomial r of x before. I'm going to call it something different this time. I'm going to call it q of x for quotient this time. I don't want to use r of x here because that will stand for remainder in chapter 16. F of x is x times q of x for some q of x in the polynomial ring. And that means x is a polynomial multiple of x. That's enough to imply f of x is an element of the principal ideal generated by x, because it's a polynomial multiple of x. Therefore, the kernel is certainly a subset of the principal ideal generated by x. What about the other inclusion? If f of x is in the principal ideal generated by x, it's essentially just reversing all the steps. That means there exists a q of x in the polynomial ring such that f of x is x times q of x. But that's enough to say f of 0 is 0 times q of 0 is 0. And that's enough to say phi of f of x, which is phi of 0, is 0. And therefore, f of x is in the kernel. Therefore, we also have the other inclusion. Since we have both inclusions being true, that's enough to say the kernel equals the principal ideal generated by x. The third question is, what do all these things imply? What's the significance of all this? Why do we care? It allows us to understand other things about what's going on here, is how a ring theorist would think about this. Just like group theorists want to classify groups, ring theorists want to classify, or you might say, understand rings. And actually, our goal in this case is ultimately to try to understand why the principal ideal generated by x, this thing, is a prime ideal in Zx, but not maximal. There's a first isomorphism theorem. First isomorphism theorem that implies now that if I take the domain of phi and mod by the kernel of phi, it's going to be isomorphic to the image of phi. I forgot a question. I forgot to address one of the questions up here. Is phi onto? I'll come back to what I was showing you there in a minute. Is phi onto here? Think about it. Give me an arbitrary integer. Is there a polynomial that gets mapped to it under phi? Pretty obviously there is. In fact, you could take the polynomial over there to be the constant term that is the integer that you're given. Like if I'm given 7 over here in the codomain, the constant polynomial 7 gets mapped to it under phi. Its value at 0 is 7. There are plenty of other polynomials that get mapped to it as well. In fact, any polynomial whose constant term is 7, we get mapped to 7 under this function. So it is onto it. That means this image is in fact all of Z. But what's the kernel of phi? We just found out that that was the principal ideal generated by X. So this factor ring, the polynomial ring ZX mod by the principal ideal generated by X, all polynomial multiples of X, is isomorphic to the integers as a ring. What does that imply? Who cares? The integers is an integral domain, but not a field. Does this ring a bell from something we did on Monday? Related to prime ideals, maximal ideals, integral domains, and fields. It should. We talked about this. We talked about a couple theorems that are pretty important in their proofs. This one, the factor ring R mod A is an integral domain if and only if A is a prime ideal. And the other one was the factor ring is a field if and only if A is a maximal ideal. That's an integral domain, but not a field. Therefore, this is an integral domain, but not a field. Therefore, that principal ideal is prime, but not maximal. Why is that important? Mostly we're interested, to tell you the truth, in maximal ideals and these factor rings being fields for the purposes of understanding factoring of polynomials. That's our main goal, because it's useful to think about factoring in terms of what are called finite fields. It's a bunch of theorems in chapters 17, 18, 19, 20. They're going to be related to all this that will help us understand about factoring. And not just using the quadratic formula, when we can and can't factor polynomials is the issue. That was an issue of great interest to people a couple hundred years ago, is figuring out all these things. And it's still relevant today. Factoring polynomials does have plenty of applications. It's something you learn in algebra in high school, and you use in calculus, for example, right? Use factoring in calculus to find critical points of functions, to figure out where the derivative is 0 and where functions are maximized and minimized. Factoring has plenty of applications. So we're trying to understand the theory of this that will help us understand it more deeply. All this stuff is relevant for that. It's theoretical superstructure relevant for understanding more deeply about when we can and can't factor polynomials.